All right. So today we are going to discuss a few things. We'll talk about three things today. One, how to run on cluster. Second, how to tune and debug. And third is how to do this Spark streaming. Okay. All right. Great. So the recording has been started. All right. So let's jump in. All right. So most of the parts we have already covered. It's mostly like a quick revisit of what we have already done. All right. So Spark runtime architecture is that there is something called Spark driver, and Spark driver talks to the cluster, whether it's Mesos, Yarn, or standalone. So it's the driver which executes your main program and takes up parts of it and sends it to the worker. Now, so Spark driver as, talks to the cluster manager. The cluster manager could be the Mesos, Yarn, or standalone. Okay, any of the three things. And as per general understanding, standalone does not mean a single machine. Standalone just means that you do not have any of the existing cluster manager such as Yarn or Mesos. You want to set up your own cluster using Spark itself. So in that case, you can simply use standalone. You will have to just run. You will have to just tell Spark in the config that these are the nodes on which the cluster will be running, and then run the same thing on all the nodes. That's it. And these nodes will talk to each other and establish a cluster, and you can talk to the cluster afterwards. All right. So Spark driver gets the work done via the worker through the cluster master. Okay. Master could be Mesos master, Yarn master, or standalone. Right. So here is a very simple thing. This we have already talked about earlier. So the driver is a process where main method of your program runs. In case of Python, the whole program in itself is the main method. All right. So is the entry point of the program. All right. And when you launch a Spark shell, you have created a driver program. So your Spark shell is the driver. Once the driver terminates, the application is finished. While running the driver, it performs the following. First, it converts a user program into tasks, and then okay, and this user program conversion of user program into task is a little complex process, and it's a little more involved process. So converting user program into task is equivalent of pig getting a pig script getting converted into the MapReduce. In the similar to pig getting converted into MapReduce, these are the two steps that happen. First, so it converts the user program into tasks, and basically based on the logical graph, as in we have one RDD generating second RDD generating third RDD and so on. So based on this, all the RDDs that are required, which are part of the graph is kind of when if you try to draw it on a paper saying A depends on B, depends on C, depends on E, and so on. Okay, if you try to draw such kind of a complex graph, that is called directed acyclic graph, kind of a dependency graph. A depends on B, B depends on C, B also depends on E, and E also depends on C, and so on. This is directed acyclic graph, a graph where edges have directions, as in A depends on B. It's a directed graph. It does not mean B depends on A. It's not a both the way relationship. So it's a directed graph. and is acyclic, meaning it does not have cycles, meaning A depends on B depends on C and C depends back on A is not something allowed. Okay, so these are directed acyclic graph, and directed acyclic graph is a very common thing in the computing world. Okay, I think we have already talked about it. And while running the main method, it performs the following. It schedules task on executor. All right, let me see if you have any questions at this point. All right, it schedules task on executor. So first it converts your program into tasks. Okay, each individual, so first converting your whole program into DAG, and then each individual unit breaking down into the task to be performed, and afterwards doing the real execution. Okay, so driver schedules task on executors, coordinates the scheduling of individual tasks on executors. Schedule. So when driver schedules task on executor, the following thing happen. First, coordinates the scheduling of individual tasks on executors. Second, schedule tasks based on data placement. Okay, mainly if the data is closer to some workers. Okay, so first of all it finds out what are the individual tasks to be executed on the executors, then it finds out the executors near to the data, and then it tracks cached data and uses it to schedule future tasks. Okay, and and afterwards, based on, because certain data will be cached, so next time, if you run a.cache, the data will be cached on individual nodes. You can use that cache. It will be using that cache later on. Okay, and then it runs, once everything is fine and running, it runs Spark web interface at the port starting from 4040. If 4040 is already blocked, it will create 4041. If 4041 is also busy, then it will create 4042 and so on. All right. All right. So executors are the worker processes that run the task of a job. These are the main units of work. It returns result to the driver. So executors launched once at the beginning of the Spark application run for the entire lifetime for an application. Okay. So basically, the executor might finish in the beginning, or whatever time it takes. Okay, and but they can be killed from the Spark application. All right. So it all depends. This lifetime part is something which is contradictory here. So there are different kind of applications. Some applications which want executors to be forever running. Okay, because there are long time running processes as well, right? And these executors provide in memory storage for cached RDD via block manager. All right, so there is something called block manager, okay, which is a part of RDD. Because so while we were talking about RDD. RDD is not really physical storage, or is all not really in memory storage. It's more like a mapping. Okay, it's more like a mapping. Mapping is done by using the block manager, saying this section of the RDD is at that particular place, and this section of the RDD is already cached, and so on. Okay, so that in-memory storage for cached RDD is managed by block manager. In local mode, the driver and executor are from the same process. There are local modes as well with the Spark. In that case, the driver and executor are from the same process. Basically, it's the same one running locally. All right. So cluster manager launches executors. So it's not the driver. Driver asks cluster manager, and cluster manager is the one who executes the real work, launches the executor, and in some cases launches the driver too. Okay, so if you are running your application in yarn cluster mode, in those cases the cluster manager will also execute the driver. Okay, and this cluster manager is a pluggable component in Spark. All right, and this cluster manager is nothing but it's also kind of application master, okay, on yarn, and similar plugin for mesos and similar plugin for standalone. So cluster manager is a component, okay, which is pluggable, and it plugs into yarn, it plugs into mesos, it plugs into the standalone. All right, so here is something that demonstrates the flow. Okay, so user on the left hand side uh, does a Spark submit, or starts start the shell and does execute an action. The request goes to the driver. Driver talks to the cluster manager, and cluster manager starts executors, and then once the process finishes, exit is called and Spark stops. Okay, so user submits an application using Spark Submit. Spark Submit launches the driver program, and Spark Submit invokes the main method specified by the user. Driver program contacts the cluster manager for the resources. Okay, and okay, the cluster manager launches the executors. All right, and driver process runs through the user application. Right, the driver sends work to the executor in the form of tasks, and tasks are run on the executor process to compute and save results. All right, and then once the work is finished, it terminates the executors and releases resource. Okay, if the exit or stop is called. All right, so if you want to run and execute a Python program, you can do this kind of job. Say for example, we are saying uh, here, create your own Python program. Here, the only difference between running things through the shell is that the Spark context instance is being created by you. Okay, you are importing the context and then saying sc equals to Spark context, and as a matter of fact, when you launch the shell, this is what happens, okay, internally, and then your program begins till here. All right, so you can try it out, you can try this program out. We have already tried it a couple of times. Just that instead of hadoop1.nobigdata.com, you have to say a.cloudxlab.com /data/mr/word count and then input. Okay, and then here also you don't have to specify. This was good only if we were running in a standalone mode, because in that case it will directly read the data from here. But since we are running in already in Hadoop and Yarn, this we don't need to give this location. It by default understand /data/mr and so on. From this point onwards, from data onwards, it will understand it as the HDFS file. And once you're done with this, we have already gone through it once. You're done with this, you save it into, say, some file, and afterwards you can launch it by saying yarn conf directory is this and Hadoop conf directory is this, and say any Spark you download, you can run it using this command. Okay, and then afterwards you can check these locations. Let me just correct it now itself before things go. Okay, so we are saying a dot, all right, cloudxlab.com Okay, so in case you want to try out your own cluster, your own Spark, you can simply download corresponding Spark, but keep it on the server. Keep it on one of the servers. Okay, keep it your folder. Okay, here this one is your, or you can just simply say, actually, you can just simply say this one. Okay, so that it will save it in your home directory. And then you can here, don't forget to change its mode to executable. Okay, or otherwise you'll have to run, yeah, I think you'll have to change its mode to executable, and then specify the yarn config, Hadoop config. You don't need to do this because we've already configured it properly, and you can simply say spark submit and master is yarn and then execute it. Also, you can do things like this. All right. All right, so you can try it out and keep it as an exercise. All right, now let me, all right, there are a few questions from Shreesh and Arpan. Let me take those questions. All right, so I strongly suggest that you try it out all of these tools. Okay, okay, so question from Arpan is, when we say Spark Submit launches driver program and main method, what is Spark Submit? I know it is a command, but is it a program or a thread or a long running process? Okay, so it's basically is not a long running process. Okay, it's basically something that submits the job and exits. Okay, and Spark Submit is something which basically, if you are running it in the client mode, if you are running master's yarn client mode, then Spark Submit will wait till it finishes. Otherwise it will just create the driver on one of the cluster node and then exit. Okay, you can try it out. Okay, it's a program which may or may not it, I don't think it's executing in a thread. Okay, and because it's not trying to run it locally, it's trying to schedule the work on the cluster. Okay, so it's a program. Okay, all right. Spark Summit runs locally and schedules work on the driver. Okay, basically it launches, in other words, and launches the driver. So okay, so Spark Summit, when we say it runs, it does not mean that it's doing all the job. It's not doing all of this job in the local node. It's basically reading this file. It's reading this file, and after processing, it's scheduling the work. So the job of a driver is to parse this data and then launch the work. Now question is, the driver who is going to understand this Python file, where does it run? It runs either in the local mode if we are running in the client mode, or it runs in a cluster mode. So you can say here yarn client. Yarn client means it will run locally, sorry, the driver will run locally, but work will be done, executors will be on the cluster. If you say here yarn cluster, that means the driver will run inside yarn. Okay, that's what is going to happen. All right. Shrishi's question is, can you explain broadcast once more? So broadcast is equivalent of caching, is equivalent to the Hadoop. What was that? When you send the data to all the nodes, it's called distributed cache. Okay. So it's equivalent to distributed cache. And what we are doing here is we have a list of common words. We are sending these common words to all the nodes, and when all on the nodes, on all the nodes, when these two words is executed, these common words will be available in every node. Okay, so that's what is the distributed cache about. All right. Now there are common flags which we have. Okay. A question from Sheesh is, so PySpark itself launches the driver until user exit out the cell. Yes, exactly. All right. Good. Good. All right. So, all right. So some common flags of Spark Summit. Spark Summit is one program which can submit work to the cluster. Okay. And basically it starts the magic just like Hadoop jar does. Okay, in the same fashion. So it starts the work. The common flags for Spark Summit are as follows. First flag is master, which we have seen here. Okay, so indicates, all right, uh, here, okay, let me just, uh, 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 so it is yarn, and there you could say in the deployment mode, there is something called deployment mode. Okay, in the deployment mode, you could say things like client or cluster. We have already talked about it once. Okay, so when you learn, so basically the master indicates which indicates the cluster manager to connect to, whether to connect to Mesos or connect to Yarn, or what to expect from the master, this config file. Okay, so once we indicate that we are talking about Yarn, then it will look for this variable. It will look for this variable called yarn conf directory, and there from there it'll pick up the config file. So you can define either of the two variables, either this or this. Okay, but for compatibility reasons, I have defined both of them. All right. So master is the flag which indicates the cluster manager to connect to. The options for this flag are described in the table 7.1. Okay. Now the deployment mode, whether to launch the driver program locally on the client or on one of the workers. In that case, you can either define deployment mode as client or cluster. Okay. If you okay, if you run it in client mode, Spark Summit will run your driver on the same machine where Spark Summit is done. In cluster mode, the driver will be shipped to execute on worker node in the cluster. All right. Next is the class. Okay. So the flag class is the main entry point. If you are running a Java or Scala program, then you have to define a entry point because there could be a big bundle of classes. All right. In our case, we just define one entry point and all the depending files will have to will have to zip. Okay, then yeah. So if you are sending your file is depending on other Python file, you'll have to define an argument minus minus pi. Okay, all these files will be shipped to every node, and wherever they are kept temporarily, that path will be mentioned in Python path, so that when Python program is running, it will be able to find all the required dependencies from here. Okay, if you want some more files to be shipped with your program, you can say minus minus file. And then if you want to limit the executor memory, how you can define this. Okay, just that keep in mind that executor memory has to be lesser than what we have defined in yarn executor, because if your program asks for bigger memory than yarn is has defined, then it won't run. Okay, so the next thing is the driver memory. All right, so Arpan's question is the deployment mode. He did not get it. Okay, so if the deployment mode, if you say client, it means, so if you remember our diagram earlier, we talked about two diagrams. One was yarn client mode and another was yarn cluster mode, right? All right, so that's the deployment mode. Okay, I hope it's clear to everyone. All right, good, good. Arpan is clear to you. On worker node, if RAM is 64 gigabyte, container size is 3, what is the max memory you can? So it's not that. It's not about how much physical memory you have. It's about it's about how much yarn executor is given the memory that you can check if you go to say a.cloudxlab 8080. There you can check the yarn's memory. Okay, because there we can limit the memory so that there you can limit the memory so that you cannot nobody can no process can go beyond what is defined. Okay, so you can see here, not here, let me just go to yarn. So if you go into config of yarn, you can see how much memory we are giving, the minimum size container and then maximum size. This is a container size. Okay. Then there will be the number of cores, maximum number of containers and so on. So basically, how much memory can a process consume inside yarn is what will dictate the memory you can define for your Spark process. Okay. All right, so you will have to define both the memories for executor and for driver. Driver is the program which is going to run for a little longer unless all the works are finished, and driver might be doing things locally on that node itself instead of getting everything done on executor. So you should keep that in mind. There might be some work that cannot be parallelized, okay, and cannot be given to executor. You might be taking some data offline and then trying to run it locally on the driver itself. So keep in mind that you can keep the driver memory different from what is executor's memory. All right. So here is a quick overview on how to bundle all your libraries that your program depends on. Okay. All right. No need to bundle Spark and language libraries, meaning the libraries which have org.apache.spark. Okay, you don't have to bundle all those libraries. Okay, you don't have to bundle all the libraries and the language libraries such as Java dot. Okay, and second is, so typically what happens is when you are doing a Spark Summit. Okay, when you are doing Spark Summit, your program might be spanning multiple files. Your program might be depending on other programs, right? And you want to ship all of those. So if your program is depending on jars, you ship those jars by using the config parameter called jars, minus jars, minus jars, not minus minus, and then or you can say dash jar. uh, and then if your program is depending on some data files, you can say minus files. So those files will be copied to the same working directory, local working directory in your application. Okay, so that when your application can say file open and give the name of the file, and it will open that file, whichever you are saying minus minus file, will be copied to all the executors before executing the process. All right. Next is the py files, a list of files to be added to the Python path of your program. Okay, this could be minus py or a or zip. All right. So these are the things. So Python users, okay, there are two ways. So I so very well remember these kind of conflicts whenever I ran even the Hadoop works. So earlier when we were not having so all right, let me take a step back. So there were some libraries, okay, which could not be shipped to all the nodes. So we were left with the option that on all the nodes we will run the installer. Okay, so say for example my program depends on some binary, say image magic. Now image magic cannot be just bundled like that. Image magic has to be installed on all the nodes, right? In those cases, a tool like Puppet is great, because using Puppet you can install a library on all the machine. Okay, or you could execute manually to all the nodes. You could go to all the nodes and say easy install or pip install and install the program on all the nodes. In case of Python, pip or easy install will do the job. Okay, or in case your Python program does not require explicit installation, you can simply say minus minus files and you can bundle. It will it will basically take your Python program and make it available to your program via Python path. Okay. Next is, in case your program is Java or Scala, you can simply submit the dependent library using minus minus depending library on which our programming is dependent. Say you are trying to email and you are depending on Java mail.jar. You can say minus minus jar spark submit minus minus jar and uh, mail so Java mail dot some Java mail dash some version number that dot jar. So that will ship this Java mail to all the nodes and make it available in Java path. Okay, all right. If you have many libraries, one is that you put all of them as comma separated, or a better thing would be you use a build tool like SBT or Maven, so that Maven will install all the dependencies together. Maven can also make a bundle containing all the libraries into a single place. All right. Yes, Arpan. This is similar to distributed cache. All right. So yeah. So copy the Spark on one of the nodes and export yarn conf directory and Hadoop conf directory and mention master yarn in the command line while doing Spark submit. No need to install on all the nodes. That is the beauty of yarn. You don't need to install yarn on all the nodes if you are running Hadoop, because yarn will make your program proliferate to all the nodes. Okay, yarn will do the magic, and that was the quality of yarn. Okay, if you are running on Amazon EC2, Spark comes with built-in script to launch clusters on Amazon EC2. If you are not using yarn and you want to use Amazon EC2's built-in capabilities, so you'll have to first create the AWS account, obtain the access ID and the secret key. Then you go to, after you have downloaded the special version of Spark for Amazon EC2, you'll have to add it the environment variable by exporting these two variables, and then create the EC2 SSH key pair and download its private key. Okay, and then okay, and then use that in your .ssh in the .ssh folder. All right. Afterwards, okay, or after, and basically whatever PEM is generated by there, you can use that while launching the Spark program. This is the okay. This is the file name. This is the file name, and this is the name of the key. This is the name of the key. So while you create an SSH key, it will ask you the name to be created, and then it'll give you the file to download. Okay, you just download it and keep it in the same folder, and then launch it. So instead of using the Spark Summit, you use Spark EC2. All right. So that's how you can run on Amazon. At Amazon Apache Mesos, actually I don't have Amazon EC2 or Mesos account. I can, we can try to get it because we already have some nodes from Amazon. All right. All right. So Mesos is So what exactly is Mesos? Mesos is a general purpose cluster manager. It runs both analytics workload and long running services just like Yarn. To use Spark on Mesos, pass Mesos colon slash slash URL to Spark Summit. That's it. And you can run it. Okay. The rest of the things will remain same. All right. In case of just like any other situations, if you have a zookeeper, you can run zookeeper and let zookeeper keep track of which nodes on Apache on Mesos are available and which nodes are down. And using zookeeper, your Spark can also talk to. Okay. So for example, instead of Mesos this, okay, instead of Mesos this, you could say instead of Spark talking to Mesos and directly trying to do this, it could also talk to multiple Mesos instances by the way of Zookeeper. How? So you could say Mesos colon colon slash slash ZK colon colon first node, okay, and so on. This is the node that on which the zookeeper is installed. This is a node on which the zookeeper is installed, and so on. Okay, so that's it. So this is the basically why do people use zookeeper, so that you don't have to keep track of which mesos node are up down, which are working, which are not working, so that your program is 100% fail safe. If one mesos is down, it can talk to another mesos, and that's called load balance. I mean, that's called high availability. We call it HA. Okay, and instead of you juggling with it, you talk to zookeeper and let zookeeper keep track of how many mesos nodes are up or down. Okay, and based on that, zookeeper will make available you the node. Now question arises, what happens when zookeeper node to which you were talking is dead? Okay, in that case you can have all the nodes of zookeeper listed here. So Spark, when we submit here, we say things like, all right, let me just try to show you the complete URL. How does it look? It looks a little confusing in the beginning, but okay. So here what happens is Spark submit first talks to Zookeeper, which is running on node 1. Okay, node 1, you could say a.cloudxlab.com. All right, it could be, and then there could be second node. Okay, in the same way, it could be, say, b.cloudxlab.com, and it could be here c.cloudxlab.com. Okay, so what exactly is happening? We are telling Spark that hey, there are three zookeeper node A, B, C, and zookeeper is keeping track of all the mesos nodes. There could be thousands of mesos nodes running. Okay, and then zookeeper will accordingly give the list to Spark, and Spark will talk to those mesos nodes which are available at that very instant. So these are the strategies for highly available. So question from C says, does whether Mesos also work on HDFS or its own file system? So it doesn't have a file system. Okay, it's just executor. Okay, in that cases you will have to talk to HDFS anyway. All right. So if you are trying to set up your standalone cluster, all you have to do is take the compiled version of Spark to the same location on all of your machines. For example, home, your name, and Spark. Set up passwordless SSH from your master machines to all the machines. Now, after that, edit the slaves file in your master and fill in the worker host name. Okay. Then you have to run sbin slash start dash all dot sh on your master. Afterwards, check the master node colon 8080. To stop the cluster, you can run bin slash stop all dash ssh. Okay, so this is the way, this is a very straightforward way. In very simple way, if you have multiple machines, first create a folder, same location on every node. Okay, that makes the life really easy. Once you have created same folder on all the nodes, download, or you can say copy the Spark on that particular folder. Now, between these nodes, establish SSH so that from your machine, your master machines to other, your master machine should be able to SSH because this master machine has to SSH every time to execute. Okay. Now, that brings us to the point that yarn master will ask all the executor to do sorry, the spark master will have to ask all the nodes to do some things, and it can do only if it can log in into that machine via SSH, because all of these, whether Hadoop or Spark, all of these systems talk over SSH. They have not designed their own uh, TCP/IP protocol. They're just using SSH for communication of any command. Okay, because SSH is extremely powerful. You can do anything over SSH. Unlike FTP, SCP, which only allow file copying, SSH allows you to execute command securely. Okay, and in many form and fashion. So that's why you could set up passwordless SSH. You will have to set up passwordless SSH from the master designated node to all the slave nodes. Okay, then In the slaves file, you fill in all the workers' host name and then run start dash all the master on your master node. Okay, and that should be good. All right. There are a few questions. Let me answer those questions. Sachin's question is between Mesos and Yarn, which one is better on Hadoop to cluster? I would strongly recommend Yarn. If you did not have Hadoop too, then you might have thought about Mesos. But I'm strongly recommending Yarn because Yarn is probably most popular, and Yarn has many application available. Okay, Mesos is comparatively new. Okay, and Mesos also does not provide any storage out of the box. Yes, similar to Hadoop, we are setting up passwordless SSH. That's correct, Arpan. So if we are setting up Spark on Hadoop cluster, then we don't need. No, we don't need. Or let me just. Yes, we do not need. Okay. All right. Billion. So in case you want to set up your standalone, you can use it. Now here is a question. If you do not have Hadoop already, start with standalone cluster if it's fresh new deployment. To use richer resource scheduling capability, use Yarn and Mesos. When sharing amongst many users is the primary criteria, use Mesos. If you have many users executing jobs, then Mesos is better. If you have few users using Yarn, then although the workload is bigger, but there are few users using a cluster, then go for Yarn. In all cases, it's best to run Spark on the same node as HDFS for fast access to storage. Okay, if you have data in HDFS, then you go with Yarn. All right. All right. Sometimes it's actually possible to even give a try to standalone on Mesos with the data locality. Okay. So what you can do is you can install Mesos or standalone cluster on all the data. So you have Hadoop running already. You have data node designated already. On those same data node, you can install the standalone cluster slaves or Mesos. All right. So that the data is available on the same nodes. Okay, it will try to decipher the local data locality based on the IP addresses of the data nodes. Okay, and that's how it works. Al- Although the best way of data locality is using Yarn and HDFS together. All right, so that was a quick overview of how to run things on a cluster. All right. All right. Now there is one more thing I would like to discuss, that is few of the configuration values. All right. Though these are not mission critical things, you can always go back and study for tuning, but it's important to know what all is configurable. Okay. What all is configurable, that's something important to know. All right. So while launching your program using Spark, you could control Spark config. So far, we have not talked about Spark config at all. All we did was we created directly Spark context with an empty no argument, which means the default config loaded from the etc configuration file is available here. Okay, so basically Spark config is quite straightforward. Okay, all right. So you can you can create a Spark config object just the way you, when you launched MapReduce program, you created the config object. In the same way, you can create your config object. Okay. So by the way of saying conf equals to Spark conf and then setting all kinds of variables into the conf. Say you want to override default port on which the Spark UI is going to run, then you can say spark.ui.port. Okay, if you want to run locally instead of yarn or yarn client or cluster, you can say spark master is local. All right, and you want to give it a name so that it is visible in the jobs with this name. Okay, you can set that, and once you have configured all the values, then you can create this Spark context, which is our entry point. You remember our SC, that this is our entry point. From here you can start using sc.text file and so on. Okay, or sc.hold text files, and there are many other functions which we have talked. Okay, so you can basically configure this way, and then once this is done, then you can move. Rest of the process will be using these variables. Otherwise, if you don't want to hard code these values in your code, you can pass these from Spark Submit as explained in the previous example. Okay, you could say here you can add things like minus minus conf and all the variables you can set here. All right, so these are the options available. The executor memory, instead of dash dash executor memory, you can set the config saying spark.executor.memory. Same thing, but in the config form. Okay, if you remember earlier, we were using minus minus master minus minus executor memory. Instead of that, you could say conf.set executor memory, or you could say minus minus conf executor.memory. Okay, so you could say spark.executor.memory in the config object. Same variables could be used. Okay, now here basically, if every executor is a dual core or it has 4 cores, you can put those number of cores here, because this is something which you know better. All right, similarly, the maximum number of cores you want to limit it to, then you can limit your program to. Then there is something called speculation. Speculation as, okay, if there's one task which is not finishing while others are finished, same task will be executed somewhere else, and let whatever finish first take the precedence. Okay, all right. So that's like duplication of effort, but that generally increases the overall duration. Okay, so this is the timeout. Okay, this is the timeout. And then you have, if you want extra options for your Java program, say you want to print the GC detail, garbage collection detail, or let's say you start on every node, you want to start a debug port. Okay, all of those extra options could be provided using this particular variable. Okay, if you want to add more class path, more extra library path, you can do all of those. All right, so we have already talked about the the components of execution, job, tasks, and stages. Okay, so you create a big job, that job creates the tasks, and every task has got multiple stages. Okay, so let's go through these works. Okay, All right, let me just try to fix it properly. All right, so all right, let me open the console. All right, so this is our console. And on the console, we are starting our PySpark. All right, now we say here, all right, so we have loaded the text file, and loading means just basically marking the RDD. Okay, so when you say to debug string, it basically gives you the details. Okay, on every RDD, you could always say to debug string. It tells you what is it that's going to do. Okay, so let's say, for example, we have loaded this text file and we have defined a function called line length, and line length, whatever string we give, let's say whatever string we provide, it provides return length of that string. Okay, now if we say llrdd equals to rdd dot map, and we have this. Okay, and we could say rdd dot to debug string will give us the detail about what's going on. Okay, you can see that python rdd at rdd python.scala, and then there are, okay, so it's talking to this particular file and so on. Okay, all right, or what could we do? Let's just see. And words dot to debug string. All right, so you can see that it's showing the, okay, let me see what happens in this case. Right, all right, let me just see more. Result dot to debug string. Okay, now it shows that map partition at this, then shuffle, then, okay, after that pairwise reduce, and then there are two map phases. Okay, so it's showing you that first it will load this data. Here you can see that it's going to load this data, and after that the map partition will happen. After that reduce by key would happen, and then pairwise RDD will be generated. Okay, and after that the shuffling will happen, and then mapping will happen. So you can see that all these steps are being shown in details. All right, so this is what is happening. Okay, so first of all we are saying sc.text file, it's talking to Hadoop RDD, then mapped RDD. Hadoop RDD is getting loaded and this mapped RDD is being created at this point. Now, when we run map, it is resulting in another mapped RDD. Then when we are running filter, it's resulting in filtered RDD. And then we are running reduced by key. And then it's resulting in shuffled RDD. Let's take a look here. Okay, so you can see there's a map partition, there is reduced by key here, and then the pairwise RDD is being generated and so on. So there are multiple steps that are happening when we are saying reduce by key. All of these plans are getting executed. So this is our RDD graph. Okay, this is our RDD graph. Why? Because shuffled RDD depends on filter, depends on mapped, depends on so on up to Hadoop file. Okay, from here it depends on it. Okay, now this RDD graph get converted into two stages. One stage where all the logic can be combined in a single shot. All the map, if you are running map 10 times, you don't need to have multiple stages for anything. All those things will get combined together. Otherwise, imagine that it's like optimizing maps. Okay, if you are writing map reduces and you have created multiple stages, each one doing nothing but mapping, meaning translating data from input to something else, then and so on. Here it's doing a great work. It's optimizing this, it's combining all of this code into a single program because all of this is happening in a transformation phase. There is nothing happening as part of shuffling. So this all of this filter, map, and then loading text file, all of this is getting converted into a single stage. Okay, it's a single stage that is getting created, and the other stage is where the shuffling would happen and the main work will get executed. Okay, so this is combining all of the things which can be done in a single shot is called an stage. Okay, so basically breaking down an RDD graph, a RDD graph is the all the RDD which are dependent on each other. Okay, like for example, words kv depend result depends on words kv, and words kv depends on words depends on RDD, and RDD is loading the data from here. So if you see, it's basically a dependency graph. Okay, and same thing has been represented here. Now this graph, this RDD graph where the dependency is there, this graph is broken down into stages. The things that could be done together easily, and these are most optimized to do it together, the multiple RDDs are combined into single stage. Okay, multiple RDDs are combined into single stage if they are all transformation. Okay, can we see stages using RDD.debug string? Not really. Actually, the to debug string can only show you the graph. The physical execution plan happens after you do the action, as well as there are ways to do it. I'll show you. I think there are ways to do it. Okay, I'll show you in as we go forward. Yes, yes, Arpan. So basically, all the operations without doing any shuffle is a stage. Yes. So also there could be a scenario that after shuffling, there are many map or filter or those kind of phases which are not which can be done on the same node. Okay, all the code that can be done sequentially on the same node, they can be combined into a stage. All right. So each task internally performs the same steps, fetching its input either from data storage if RDD is an input RDD, or an existing RDD, or shuffled outputs. Okay, so fetching an input. So every task does these following things: First, it fetches the input, compute the RDD, and then writes the output. Okay? Okay, performing the operation necessary to compute RDD that it represents, for example, filter, map, or input data, or performing grouping or reduction. Okay, so basically, if you think about task is nothing but first phase is reading the data, then running a code, and then saving the output into RDD or somewhere. All right. So here is the whole summary of execution again, whatever we have discussed earlier, whatever we have discussed earlier. Okay, so user as in me and you define a DAG as in when I say RDD1 equals to RDD dot filter or RDD2 equals to RDD1 dot flat map or map and so on. So user 1 defines the directed acyclic graph. Okay, because you are saying my RDD2 depends on RDD1 depends on RDD and so on. Okay, so uh, that's our DAG creation phase. Okay, whenever we say action, when we call an action that forces the translation of DAG is in directed acyclic graph, DAG into an execution plan. All right, when you call an action on an RDD, it must be computed. This requires computing its parent RDD and parent's parent and so on up to the input file. Okay, so as soon as we say action, Spark scheduler submits the job to compute all needed RDDs. That that job will have one or more stages, okay, which are parallel waves of computation composed of tasks. All right, each stage will correspond to one or more RDDs in the DAG. And a single stage can correspond to multiple RDDs because of pipelining, because we are combining multiple RDDs into the stage. Tasks are scheduled and executed on cluster. Okay, so stages are processed in the order with individual tasks launching to compute segment of RDD. And once the final stage is finished in a job, the action is done. So every stage is executed inside the task. So pipelining, so Arpan's question is, what is difference between pipelining or staging? It's the same thing. Okay, it's the same thing. Pipelining or staging means the same thing in context of Spark. In both the cases, the dependency graph of the whole logic which you have written is getting converted into stages. Okay, it's getting converted into stages so that each stage will run inside a task and will accomplish what it has promised you. All right. So you can go to Spark Web UI. For me, let's just see if I'm able to access my logs. Okay, let's see. So when I started, it says here that it's already in use. It's already in use. Okay, 4040 is already in use and probably it has started on 4041. Yeah, mine is started on 4041. So instead of using this IP address, you should use, say, here we are on h5 dot 4041. Sorry, we have to use a URL like this. Okay, it says the total uptime is 14, which means my console is up for 14 minutes. It shows the storage, and this is the environment. You can see that we are using 1.8 Java, and the all the details about Spark. Okay, these are the variables which will help you in debugging what kind of problems are you're facing. Okay, all right. So this is the thread that's running at this point of time. So driver is the console which we are running right now. The PySpark console has run a driver, and this driver is running at this address. Okay, and at any point of time you can take the thread down. Okay, it shows you the details about the threads, how many threads are running and what's going on. Okay, so this UI is quite useful for finding out what is wrong with our installation. And so far I don't think there are any storages. If we try to run a cache, if you try to run a cache, will it work? If we say result.cache, okay, so will it have something, or there is something wrong with it? Or we can say result.persist, result dot result dot what was that, collect. Where did it go? Yeah, when we are running this, then it is showing you the memorized, serialized, replicated. Okay, you can see that it's a Python RDD which has been cached. Okay, 100% of it has been cached into the memory. We have consumed 1.2 MB. Okay, you can see first we said collect also called reduce by key. Once the job is over, storage will vanish. No. Okay, unless you explicitly say what do you call, I think it's called unpersist or uncache. I'll have to find that exact word. All right, so this particular thing will remain in the memory as long as the driver is up, so that even afterwards we could use the same RDD inside another RDDs. And that's the purpose of the cache. Brilliant question. All right, so you can either look at the UI or you can look at the log files produced by driver and executor process. All right, and interestingly, when a Spark process runs, it gives you the log URL, and it hooks into your usual yarn flow. You could go to the history server and check the URL. Okay, all right, so we have already used these. So a quick overview of where is the logs. Okay, in Spark's standalone mode, application logs are directly displayed in the standalone master's web UI. Okay, if you are running in the standalone mode, it will show you in the web UI here itself. Okay, and let me see. Okay, we have jobs. There is one job which was running. Okay, it did collect, and inside collect there was all the details what was going on. Okay, and it will show you all kinds of matrices, whatever you want to see. An event timeline also, it's showing you what happened first. And whenever you encounter something strange, you should generally look at these details, and these details will give you a great idea. All right. What is it going on? Oh, we are scrolling through it. Oh, I actually zoomed in. You can actually zoom in, zoom out here using mouse. Okay, on these timelines. So you can see that there are two tasks, task 1 and task 0. Okay, task 0 took a lot of time, while task 1 finished fast. And what do we have here? Okay, there are two tasks, 0 and 1. All right, you can see that. All right, stages, DAG visualization, something happening here. All right, you can see. All right, can enable zooming and all. Okay, so yeah. Let me try to pull it. So it says collect has succeeded, driver was added. Okay, so you can go through this. All right, so there are two stages. Okay, and stage 0 and stage 1. For collect stage, there are two tasks for each one. There are two tasks each. Okay, and so on. All right, you can go through it. All right, so to look for the logs, if you're running in standalone mode, okay, the UI will be showing you the logs itself. This web UI, you can hook into it. Okay, so I have put in somewhere. Okay, and they're stored by default in the work directory of Spark distribution on each worker. In Mesos, logs are located on work directory, and in case of yarn, you could look at the yarn logs and give the application ID, and it'll show you all the logs for yarn. All right. So when you are optimizing the performance of Spark, here are few of the things you have to keep in mind. One is label of parallelism. How many partitions do you want in essence? Second is serialization format. Third is memory management. And fourth is hardware provisioning. We'll look at each of them. So how many partitions do we need? Okay. By default, a single task would be executed per partition. Okay. By default, single core in the cluster is to execute. Okay. By default, the number of cores to utilize is 1. A good degree of parallelism is based on underlying storage. Okay. All right. And in case of SDFS, generally one partition per block is created. That is that is the default behavior, and it's good because if you have many partition on one particular SDFS block, there will be too much of data transfer. Okay, so if you have two less partitions, very small partition, too few partition, as in for even 1 GB, if you have only one partition, okay, so most of the resource will be empty in your cluster because one task is created per partition. All right. If you have too much, then there will be overheads because of data transfer. Okay. If you have too many tasks running, there'll be overheads. Okay. So that's the first thing to understand how many partitions are there. Okay. Although all of these things could be configured from the config object. Now, how to control parallelism? Okay. All right. So most of the shuffling first is the more partition you have, more parallel tasks will be executed. Okay. So it's okay to repartition sometimes when you want is if your work is very intensive, if your work is very intensive and you want that to be divided into many task executors. In those cases, it's okay to repartition a particular RDD into more partitions, say 1,000 partitions, okay, so that one task get executed on every partition, and there will be too many tasks executed. Second, the shuffling operations. The operations such as reduce by key and others accept the degree of parallelism in the parameter. Okay, and to efficiently shrink, if let's say you realize that there were too many partitions in the input and you want less number of partition, less number of parallelism, you can use coels, okay, over repartition. Because okay, because what happens in case of repartition, there might be repartition might be a little less efficient. Repartition is great when you want to increase number of partition, but to decrease number of partition, it's better to use coils, collies. Okay, all right. So, question from Arpan is, how can we specify how can we specify size of the partition? We don't specify size of the partition. Instead, we basically specify number of partition on input data, and if you divide that total data by number of partitions, that will be the individual size. Okay, or we have some by default, as I told you, the block is same as the one partition is created per block by default. All right, or do we have number of partition equals to number of execute? Yes, by default that is the behavior. It's not, it's total number of cores in the cluster. Okay, it's total number of cores in the cluster. Billion questions. All right, so the level of parallel, let's say we are reading a large amount of data from Amazon S3. The filter operation is likely to leave a tiny fraction of the data. Okay, let's say you are doing filter on S3. What will happen is the resulting RDD might be fairly empty. But interestingly, the resulting RDD will be the same size as RDD of the parent, but many empty small partitions. So you should improve the performance, although there will be no logical problems, but partitions will be inefficient unless you shrink it by using coalescing. It's more like, the what do you call it? In case of Windows, when the disk gets really big gaps, you run this tool, disk defragmentation. Okay, so coalescing basically is equivalent of defragmentation. All right. So here's an example. You are loading your data from S3. You're saying input.get number of partitions saying these many. If you filter it, still the number of partitions will remain the same. Okay. Therefore, although most of the data is removed, meaning each partition is containing only few records. Okay. Still the partition will remain the same. So in these cases, to reorganize the data, you should generally transfer the data in order to keep it clean. Okay, so you can see here you should execute calls like this, calls like this. I don't know how to pronounce this word. All right, now, all right, let's try it out with our example. Okay, let's try it out, and we would say a dot cloudxlab.com. That's okay. All right, let's try to execute this. Okay, let's try to execute it and test it out. Where is my console? Here is my console. I've loaded the data and I've loaded the data and I'm checking the number of partitions. 2. Okay, and then I'm saying filter. I'm saying filter, get number of partitions. Okay, all right. So still, even though the total number of records in RDD1 is quite few, still the data is quite few. Still the data is in the partition there. Okay, so what you do is you basically shrink the data. Here we are saying find out all those lines, those are starting with this. Okay, so let's say we have, yeah. So if we say colis, then it'll have only one. Okay, so and you can say get number of partitions is one. All right, so this way you can reorganize your number of uh, partitions. All right. All right. The other consideration for optimization is serialization format. So while transferring or saving objects, it these serialization is required. Okay. Okay, serialization is needed while we transfer the data over a wire or we convert the data into bytes at any point of time. Wherever we are converting the RAM into a sequence of bytes. These bytes could be for transferring over the wire or for persisting into the disk. Okay, so serialization is needed, as in how do we convert array into the bytes, or how do we convert a string and a big object into bytes. That is serialization. And whenever we are sorting, shuffling, saying reduce by key or order by this or by that, at every point of time you would require shuffling. And when you shuffle, the data gets transferred from one executor to another. Therefore, the data is getting transferred over the wire, and therefore serialization becomes important. Okay, by default Spark will use Java's built-in serialization. So this example where it's a contact detail of George Hill, that's basically a class object which loaded into the memory, and when we transfer it over the wire, it's like number of bytes. Okay, there are many serialization formats out of it. Cryo and protocol buffer are very fast. So prefer either of the two two formats for serialization. Okay. Yes. Arpan's question is, do we require serialization in shuffle phase? Yes. Because when we shuffle, whenever we are doing sorting or reduce by key and group by key, everywhere there is a shuffling operation. Okay. And whenever there is a shuffling, there is a transfer of data from one machine to another, and therefore there is you have to for the something for data to be transferred over the wire, we have to convert that into bytes. All right. So cryo is one serialization format. Okay. Spark also support cryo because it's pretty fast and more compact, but it cannot serialize all the objects out of the box. Okay. almost Almost all applications will benefit from shifting to cryo. To use it, you have to just say in the config, you have to say set Spark serializer to org.apache.cryo serialization. For the best performance, register classes with cryo. Because what does cryo do? So any class you want to convert, okay? Any class you want to convert into an object, you should register that class with cryo because cryo optimizes the class. Okay. Also, generally your classes need to implement just the Java serializable interface. Okay. So Arpan's question is, what is the default serialization format? By default, it uses the Java serializer. Okay. And for Hadoop sequence file, it uses the Hadoop input format. All right. So does Cryo comes bundled with the Spark? Okay. Not really. You have to probably put the jars of Cryo with Spark. Okay. You have to just put it in the conf folder. All right. So, all right. The next part. So we talked about few things. First one was parallelism. Second one was serialization format. And third one is memory management. Memory management is so storage is generally not in the memory unless you explicitly say persist. If you say persist, then RDD will be kept in the memory. Okay. And in case you said persist over a very huge RDD, which does not fit, okay, then most older partitions, the partitions which were really old, out of the whole partition, they will be dropped from the memory and it will be noted how to generate those partitions. Okay. And whenever needed, they'll be computed again. So by default, 60% of the memory is dedicated to RDD. And generally, it's better to go with persist, memory, and disk. Because what happens is that when you say persist, by default, the persistence happens in the memory. And and in case it's not fitting into the memory, it won't persist at all. Those partitions will not be persisted at all. In those cases, it's better to go with persist and disk if there are a lot of computations involved. And for shuffling, when you are shuffling from one to another, Spark will create intermediate buffers for storing shuffled output data. Okay, and for this amount of memory, which is limited to the shuffle memory fraction that you can increase at later point of time. Okay, by default this one is 20%. So total memories 60% is dedicated to RDD and 20% to shuffle and temporary data, and users code whatever logic you have written, it'll consume, it'll that only 20% of the total memory is given to it. Okay, the overall Java memory heap, which is for the executor. All right, so user functions can require sometimes a substantial amount of memory. They can consume everything out of, okay, total minus above 2. Let's say, okay, okay, by default user code runs in 20% of the memory. Right, okay. No, Arpan's question is this 100% memory is 100% of RAM? No. The total heap that you have, uh, the total memory of JVM that you have started the executor with, it is that memory. Yes, that's right. Okay. So the hardware resources you give to Spark will have significant effect. The main parameters are the amount of memory given to each executor, number of cores every executor is having, and total number of executors in the cluster. Okay, and then total number of intermediate disks. Okay, okay, and the executor memory which you have provided. Generally, applications benefit from more memory and cores. Okay, and with respect to hardware, Spark is fairly comfortable with linear scaling, meaning you add twice the resources often will make your application run twice faster. Okay, and that is the dream of any distributed computing. The dream of distributed computing is number of the time taken to do something should be reduced to half if we add one more computer. Okay, and if it should reduce to 60% if we add one more, from 2 to 3. So it should basically, if we have two computers we add two more, if your application runs in half of the time, that is the dream, and Spark is able to achieve that. Okay, also if you are trying to have really huge RAM, for example 200 gigabyte RAM, in those cases the garbage collector of Java might take huge amount of time. Okay, so do not go for really high memory in the executors. It's okay to have a smaller up to 64 gigabyte. Otherwise, if you have each executor beyond 64 gigabyte, it's going to be tough for GC, because GC has to run every now and then, has to go through all the objects. If there are too many objects loaded in the memory, GC itself might consume a lot of resources. All right, so that's pretty much about optimization and configuration. Now we will start the Spark stream processing, and along with the demo after the break. All right. All right. Is everybody back? Can we start now? All right. Gridhar, Arpan, Sachin, Shekhar, Shrish, Valentin. Can we start now? All right. So let's start with our usual discussion. So I think part of it, Valentin, you must have attended already. But today we are going to go into a little bit more details. All right. So let's jump in. Okay. So before we start, has been this word called streaming has been heavily abused. Okay. So there are many more connotations of streaming, starting with, um, let's say, a command like sed. Okay, what does it mean by sed in Unix? It basically filters some data. You can replace some data, and you can do all kinds of data churning. So SED's full form is actually stream editor. Okay, so whenever we pass data through SED, that is also called streaming. Similarly, in case of Hadoop, if you are passing data through a Python program, that's also called streaming. Similarly, in case of Pig, when you pass data through a program, that's also called streaming. Watching a movie at YouTube is also called streaming. And so, similarly, there are many more misuse of the word called streaming. Okay, in general, streaming means something when the data is traveling at a very fast pace. Okay, so okay, so in this context, when we say stream processing, or say event handling, or there are many more scenarios where when you want to handle the data at a very fast pace coming from different kind of input formats, where you do not know for how long the data is going to be coming. Okay, so most of the stream processing applications are running forever. They are listening to the stream, do the computation, and give the result. They keep on running forever. If So they keep on consuming the data whenever it's available. Otherwise, these stream processing, they wait for the input data. That is the quality of stream processing generally. Okay, these are long running processes, or you can say forever running processes. Okay, so it's a in case of Spark, people realized that Spark is fairly fast and thus can be used in a distributed Spark distributed processing of the streams. Okay, and that's where the Spark comes in. Spark says that we can basically, as long as you can convert the input data into RDD, I can process. So the way it happens is the input data that's coming at a very fast pace, the API keeps on converting that data into temporary RDDs, and then run your logic against those temporary RDDs, and then it gives the result, and then again new temporary RDD comes into play because new data has come in. Again your logic gets run. So now you must have realized by this example that your code executes multiple times. The driver executes your code many more times because there are new RDDs being created every second, and therefore the your code, your driver code gets executed many more times. All right. Okay, let's just take a very good use case. I'll take the use case which I was working on at Amazon. So at Amazon, there was this scenario. Okay, so how many of you have no you have bought things from Amazon? How many of you have already bought things from Amazon? Okay, Arpan has, Sekhar has, Valentin have. So so Sachin, have you bought anything from Amazon yet? All right. So probably all of you have all of you have bought things from Amazon. Okay. On on Amazon, the page which contains the buy now button, that's something which I was owning. And and on that page, the image which is shown on the left hand side is something I was to optimize. Okay, so that image gets computed or selected out of that image gets selected out of many images. The image which is shown at the left hand side. Okay, I'll show. Let's say here we have. Okay, so on this one, let's say this one. All right. So you see on the left hand side there is this image which is shown. This image is selected out of hundreds of images. Okay, and there are for whole of the Amazon there are millions of such images. Okay, so this image has to be improved and selected out of lots of many permutations, lots of many situations. Also, every time the image gets uploaded or any of the criteria changes, okay, we have to recompute and reselect such image. So on one end, okay, so here is the vendor. Okay, so vendor uploads or modifies any attribute. Okay, that's one end of the game. Okay, that's one end of the game. And then, so vendor has uploaded or modified any of the attributes of the product. Okay, then those changes would be in the queue. And on the server side, we need to reselect the image. Okay, and happening this is happening for many more users. Okay, so instead of as soon as vendor submits the changes we start reselecting it. Instead of that, what we have done is we have created a queue. Okay, so changes for first user, changes for second user, and changes for third user, changes for the fourth user. All right, and we select this logic, this particular piece of logic, okay, is run on many more machines than you can imagine. Okay, let me just make this way. Okay, so here is the processor. There is one processor here, and there is ouch. Okay, let's imagine that there are many processors doing the same job over and over. All right. Okay, all of these are actually reading the data. All of these are reading from this end. Okay, and then these are all of these nodes are basically producing output like this. Okay, okay, so once we have done this, the data gets stored in S3. All right, so you can see that everywhere you see this, so here, and here, everywhere the data is getting processed. This one is say running the first updates, and here I'm just saying there are many vendors upload and modify any attribute. All of those, there are many more vendors that are putting this data into this queue from all across the world. There are many more vendors. So on one end of the queue, this is called SQS queue. Okay, so this is the typical architecture. All right, let me take a step back. There are many vendors across the globe who are making the changes to the data, and those changes are being pushed to SQSQ. Why? Because it's not physically possible to just dedicate one executor to all of the vendors. I mean, just like that. You have to have a proper mechanism, because what happens in case one executor fails? So for all of those kind of difficult situations, it's better to take those changes, push them into SQSQ, and let many executors consume data from the other end of the queue. Okay, so this data kind of keeps on flowing from left to right. This data kind of keeps on flowing from left to right. Okay, so I'm just making it. Okay, so you can see that the data is flowing from left to right. All right. So this is what happens in case of this particular processing. Is this clear to everyone? Arpan, Sekhar, Valentin, Sachin, Shrish. Alright. So on many machines, we are running this selection algorithm parallelly and then saving it to S3. In case any of this machine fails, this packet will come alive again back after some time, and then somebody else will consume it. Okay, so that way nothing fails in general. So this framework of consumption and executing same logic on every node, I wrote it in a custom fashion, because none of the existing storm or something we were able to put it in production because of various reasons. So this framework, which consumes the packets from the queue, is something I wrote at that time, and it's being used by many more people in across Amazon. All right. Arpan's question is, in this one product's images are uploaded concurrently. They may be, because there are many vendors who upload images. They might be doing it parallelly. All right. Also, please note that images are not here. Images, the vendor uploads images to to say to basically same place as S3. Okay. All right. Here is only the metadata such as size of the image, the rating of the vendor, how many times in a day it's doing that. Okay? So does it make sense to you? All right. So this is the one example of architecture. There could be many more examples of stream processing. There could be the one which I just did for Dell, whereby what we were doing is their e-commerce system, the Dell's website, it sends a lot of events. So those events were being pushed into queue, and we used Spark to consume data from that queue, and did a basically prediction of or analysis of how many records are being processed per second, or whether a given purchase is a fraud or not. Those kind of things we just did with Dell. So that was a Spark streaming example. All right all right so basically, in case of Spark streaming, uh, Spark streaming is done by the way of a library called streaming API over Spark. Okay, what does streaming API do? It basically converts, takes the input and provides you something called D stream. It's a continuous stream of data. Okay, so the workflow is Spark Streaming receives in live input data from various sources. The sources could be Kafka, Flume, HDFS, ZeroMQ, or Twitter. Okay, so you can consume the data from HDFS itself, and how does that happen? You basically load the folder, and whenever new files are created in that folder, that's considered as if the new data has come in. Okay, so basically the workflow is Spark Streaming receives the data, they convert it into batches, and that batches get processed by Spark engine in the form of stream. Okay, so internally the stream is represented using an RDD of this form. Okay, so you can think of the input data that is coming in, which might be coming in per milliseconds or whatever format, that gets converted into RDD. Okay, so you can think of RDD1. First RDD that got created would be for first second, all the data that was received in 1 second, first second. Then second RDD would be created for the second data, and so on. So you can imagine that in an hour there'll be 3600 RDD created. Okay, so this is how the magic starts. First, taking the input data, converting it into RTDs. Okay, that's happening internally by DStream. Then, instead of you managing individual RTD, Spark Streaming takes only the logic from you, and then it executes again and again on every RTD, and print out the results. All right. So okay, so the original stream of data. Okay, I will do the comparison afterwards. Okay, all right. So question from Arpan is why not Storm? Where Storm and Spark are better than each other? Okay, all right. Let me take it up later on. Let me answer your last question. So his last question is, let me put it here. so that I don't forget. All right, so let me answer his first question. So RDD is set of events in X seconds. So it's a micro batch processing, right? So honestly, most of the stream processing is about converting a continuous data into mini batches and then through, run the logic through it. Okay, so you can see here. All right. So you can see on one end, time one, time two, time three, and we have windows here, and then we are getting windows of the stream. All right. On top of it, uh, Spark Streaming also provide you something called Windows operation, in the sense that over multiple RDDs run you can run your logic. Okay. So for example, if you want to say reduce by key and window, and you could say this. Okay, it will essentially concatenate the data from the two RDDs, multiple RDDs under this duration, and then run the reduce by key operation on those. All right. All right, so let's start the example of Spark streaming. Okay, is everybody with me? Let's try to run it. Okay. All right. So from PySpark context, all right, we say this. All right, let me try to save it. All right, let me go to console. All right. So what exactly is happening here? So first of all, we are basically doing the import. All right, and then what are we doing here? Then we are creating this Spark context to the local. Okay, we are trying to run it in the local mode. All right, and then all right, we are saying that SSE equals to streaming context. Okay, and here we are providing a window of 1 second. All right. So we are saying create a streaming context from this Spark object on top of it. We are basically SSE is the Spark streaming context, and Spark streaming context, which is basically a wrapper around Spark context. Internally, whenever we do something, it's going to call Spark and do the same thing on that particular temporary RDD. Okay, and then here we are saying SSE, please open text stream to this. Okay, which means it will start reading data from this. Okay, this port. That means we can connect to this port and start writing to it. All right, so let's try to create it. Okay, let's try to create it, and let me create my folder. All right, let me just create my folder. Spark streaming. Okay, let's call it All right. So that was initial one. So here we are saying lines is our continuous stream of data. So lines is the D stream RDD kind of. It's kind of a D stream which pretends like an RDD. Okay. On the D stream we can call methods like map, flat map, and others. It tries to mimic the behavior of an RDD. Okay, though it points to the temporary RDD which is created by dstream. So every time you call flat map, this flat map is going to be called on every time our program is running against this temporary RDD. Okay, temporary RDD as in from the input stream, every second or whatever window you choose, every second it's going to create an RDD, and on that RDD, these methods flat map and map are going to get executed. Okay, here we are saying words equals to line flat map and so on. Here similarly, the reduce by key is going to get executed every second. All right, and this method word count.pprint is going to run every second. Okay, on every temporary ID. Okay, now after once we have created the whole logic of flat map, map reduced by key, we can say this pprint is also not going to do anything right now unless we say sse dot start, and then we say wait for termination. Okay, so let's try to understand what's going on here. There is somebody who is listening, and there's somebody who is saying right now this program when we say when we say here socket text stream local host and we say 9999, it means that it has opened a socket at this port. It has started listening on this port here. Okay, now we have to say something to it, only then it will do something, right? And therefore therefore we'll have to run. Okay, we'll have to connect to it. All right, let's see if we have the data available here. Okay, it's saying that it's available hadoop fs minus ls. Okay, so let me show you this part. Okay, let me copy these to spark streaming dot ex. Okay, you can say hadoop fs minus copy to local slash data slash spark. All right, so the data is here. Let's take a look at these programs. I'm using a program called vi. You can see here. All right, you can see it says that from Spark import Spark context, run it locally, and wait for localhost at this port. Okay, and then wait for termination. So, and let's have a look at what's going on this machine. So let's not run it this way. I've written the whole command in this shell script. Okay, the vim is not installed. Okay, now you can see that spark submit entry.py. Okay, entry, where is entry.py? Do we have entry.py anywhere? Okay, it's not there, so we will have to rename it. Okay, So we have this program. Okay, and also note this syntax is this program, this shell command is nothing but saying please submit this particular file and then two angle bracket dev null. What does it mean? It means if there are any errors, send it to dev null. And what is dev null? Dev null means a device which can consume anything, which basically listens to everything and does not care about it. It does not store anything given to it. And after that, we start talking to it. Okay, let me just copy it and try to run it. Also, since we are talking about two different people, one listening and other saying, so we should open another terminal. Let's open another terminal. And in this terminal, what we're going to do is we are going to be the speaker instead of listener. Okay, all right, let's try to do it. All right, so let's, instead of running through script, let's just copy the command, although it's not a big deal. Okay, so let's see if we are able to talk to it. All right, you can see that it's trying to consume and there is nothing being executed at this point. Okay, this p print is what is printing this data at every second. So you can see we could talk to and see localhost and say 9999. Okay, it says that the connection is refused. Just a second, let's take a look. 9999. Okay, okay, and c minus. Okay, okay, so yeah, all right. So it's actually like NC minus L. We are listening on this port called. All right. So you can see what's going on with this. Here, you can see it has tried to count the word every second. Okay. All right. What we can do is let's say we want to run tail minus f, and we could say things like where, or we could say syslog. Sorry. All right. What would be the good place to generate? Let's say PS. Okay. And what? How do I? Let's say top. Okay. So top keep on generating the data, and we are passing top's data to this command. You can see every second it's consuming the data from top. Okay, and what does top do? Top basically lists down all the processes. Okay, you can see every second it's basically reading data from 999 and then it's trying to compute the frequency of words. Sounds interesting to you? And the real magic would start here. Okay, I'll show you some more things. See, I've ended the process there. It took some time to reflect here. Now, there is a command called yes. All yes does is it prints y forever. Okay, it's not listening to me anymore. All right, it has, I think it has printed it so many times that, yeah. All right, let me log in again. Okay, so let's again run this command called nc and pass yes command to it. So the output of yes is going to nc and it is being coming to here. Now you can see per second these many times y has occurred. Per second it's around 3 lakh. Okay, you can see it has occurred around 10 lakh this time per second. Okay, so this kind of performance can be measured, done using Spark. This is being executed locally. It's not being executed on the cluster. Okay, this can go drastically high. All right, so you can see clearly what's going on. Yes, it is the word count version for 1 second worth of data. All right, so even after I have cancelled the job, there are a lot of data still lying in RDDs and it's consuming it. Okay, so I strongly recommend all of you to give it a shot and give it a try. Okay, so we were on one end, this guy, we executed nc minus l at this port and typed something. On the other side, this is what it did. Here we say things, here it listens. All right, sounds good to everyone? So if you say yes, it means it'll lot of data would be there. See, still there the data lying in the memory, still counting. Now it became empty. Sounds good to you? Oh, it's still counting actually. Is anybody else pumping the data other than me? Yeah? Is any of you pumping the data to it? No? Okay. Question from Arpan is, when will the logic terminate? Never. So this that is the difference between normal programs and streaming programs. Streaming programs never terminate. All right. Okay. So in case you want to get started with Maven or Java, you can basically create a complete project using Maven and then edit the pom.xml and add one more dependency called Spark Streaming, this, and put a version here. For right now, we are using 1.5.2. Okay, and then once you are done, you can simply say maven.package and it will package everything. All right, sometimes, yeah, sometimes you can you want to depend upon Kafka. Basically, you want to consume Kafka, Flume, Kinesis, and Twitter. All you have to do is add a dependency here for those libraries. Okay, you can simply add the dependencies, and that is good enough. All right. For Python, it's better to download the jars binary from Maven repository. If you are into Python, then instead of handling through the Maven, it's better to just download the data these libraries directly from Maven repository. Okay, because in Python we are going to use the same ones. Okay, here I think we are using 1.5.2. You can see here, let's say PySpark. I hope it has ended. Oh, nice. Now it has ended. Good. Basically, ended in the sense. So, yeah, we are using 1.5.2. All right. So, let's go here and say 1.5.2 and click on search. All right. So, you can see all the libraries related to Spark for this particular version. Okay. All right. So, all right, so let's take a little more detailed walkthrough. All right. So first one is initializing streaming context. So first of all, you import PySpark. From PySpark, you import Spark context. Then PySpark.streaming, you import streaming context, and then you create an instance of both of those. Okay. Next is okay. So this app name is something which is displayed on the UI. All right. So after you have defined the context, you have to do the following. First, define the input sources by creating input D stream. So this is what we are calling a D stream here. Okay, we are calling a D stream here. Now afterwards we can apply transformations, and then once we have applied transformations and various kinds of logic, we can start the process using streaming context dot star. Okay, and this way the whole process will start. Unless something serious happens, it won't end. Okay, it will basically it will either has to be stopped manually, or it ends when there is an error. Okay, and in case you know when to stop on a certain logic, you could also say streaming context dot stop. All right. All right. So do not use local or local one as the master URL, because it only will have single thread. Okay. So the consumption will be there'll be no thread left for processing the received data. So use two at least here. Okay. Okay. In a cluster, uh, number of cores allocated must be greater than number of receivers, else system will receive the data but will not be able to process it. All right. So the sources for Spark streaming could be anything, starting with the TCP IP connection. The one we just did, it was a TCP connection, socket connection, which opened the data or data connection and read from that connection and kept on running it again and again. Alright. The next is you could read the data from file or folder continuously as the file is being appended or more files are being added into the folder. This Spark streaming will keep on running your logic again and again. Streaming based on custom actions. Queues of RDD as a stream. If you have another RDD which is being created by some process, you could use that as the queue for another Spark streaming. And then there are advanced data sources such as Kafka. All right. So text file is very easy, specifically when you're dealing with data accumulated via Flume. This particular way could be great. Okay. Or some other mechanism. If the files are being created in a folder continuously, then this mechanism is great. But please note that if you are appending to the file, this mechanism will not bring the fresh data. Okay, it's good for reading files or any file system compatible with HDFS API. Spark streaming will monitor this folder called data directory. It will process any file that have been created in this directory. Directories within directories are not supported, so you keep all the files at the top level, and the files must have the same data format. Okay, files are created by moving or renaming them into data directory. Okay, once moved, the files must not be changed. Okay, if there is an old file, you just added some data to it, that change will be completely ignored. That file will not be picked. All right. Or okay, so keep that in mind. Okay, you could have more aka actors as in the custom functions to to create more data. In that case, you can create your own custom receivers. Okay, you could also use queues of RDD as stream. This is for testing Spark streaming application with test data. Create a D stream based on queue of RDDs, and then you can run your logic. All right. The other advanced sources are interfaces with non-Spark libraries. Some of them are complex dependencies, such as all right, such as Kafka and Flume. So as of Spark 1.5.1, Kafka, Kinesis, Flume, and MQTT are available in Python API. All right. So let's talk about Spark streaming with Kafka. Okay. So I have demonstrated you a very trivial version of stream processing, which was using the TCP/IP connection. Our Spark streaming code was reading from a port on 999 on localhost. And we created that port by using a command called nc. We said nc-l listen on 9999. And whatever we type there, whatever we give the input to this nc command, it's going to give it to our Spark streaming. So earlier we did was we passed the output of yes command to nc, which was listening on 999 port, and and the nc printed whatever it receives in the input in its output stream, and which was read by that output stream was read by our Spark streaming processor. Okay, so nc yes pipe nc was a way to emulate TCP/IP connection. Okay, all right. Now here is the real integration. So what we have to do is we have to read data from Kafka. Kafka is a, what exactly is Kafka? Kafka is a publish subscribe messaging. It's distributed, partitioned, and replicated commit log service. Kafka is a powerful queue, meaning it runs on many machines. In case any of the machine fails, the work is delegated to somebody else, and and therefore is quite powerful. Also, the data is replicated on multiple machines. In case one of the machines fail, there is always a backup. All right. And Kafka could be used as a pub sub model as well, meaning it's an event queue. As an event queue or event bus, we can use Kafka. Okay. All right. For integration with Kafka, you need Zookeeper. You for this particular integration, you need Kafka, of course, you need Spark, of course, and you need Zookeeper. All of the above are installed by Ambari if you are going with Hortonworks data platform. Kafka library you need to download from Maven and is also available in /data/Spark. Okay, so first download the Spark assembly here. All right, let me just download the two version. Okay, so let's just take the assembly. Sounds good to you? Okay, we have Spark streaming assembly here. This is what we wanted. Yeah, we could have clicked on this. This is good. All right. Instead of downloading from here, I'll say something. Okay. So let me just go to my console. This is my console. Exit from here and say wget. Wget is a way to download something. Okay. So let me open this and copy link address and download it. Okay. Let's download it. It's done really quickly. All right. It is good. It's an archive. So things look good. And also, in case you want to find out the signature, these are the signature, or you can see the MD5 signature. Okay. Let's see. We say MD5 sum for Spark. Okay. Is it same as this one? Yes. Okay. Correct. All right, so signatures are same. That means the download is good. And all right, so yeah, now we create this program called from PySpark import Spark context with we create with these details, and then we create the streaming object. All right, and then we run it. All right, let's try to create this program. Okay, and how do we create? We write, all right, I'll go through this code once more here. that'll be more useful to you. Good. Yes. All right. So yes. So objective is to do the word count via putting the data into a queue. Right now, what happened was in the previous example, were whatever we were writing to whatever this command called nc was printing to a std out, it was being read by Kafka. It was being read by Spark Streaming, not Kafka. Now, what we'll do is we will push the data to Kafka. From Kafka, Spark Streaming will read. Okay, so the first step is here. Let's take a look. First, include all the things that are required. Okay, next is uh, okay, so have all the includes in place. After that, we create the Spark context with a different name. Okay, right now we have nowhere mentioned that we are going to talk to Kafka, except for the name, it doesn't matter. Next is we are taking the name of zookeeper quorum. Okay, all right. So in case you're confused about what is zookeeper quorum, let me try to draw a good diagram. Okay, so zookeeper quorum is something like this. Okay, zookeeper. Let me just write zookeeper. Okay, so there are users like you and me. Okay, or you can say, let's say our Spark streaming, okay, is here. It's asking to zookeeper which nodes are up for using for using for using what do you say, which nodes out of all of these, which nodes are up. Okay, for what do you say, Kafka. Okay, which, or you can say which Kafka nodes are up. Okay, so the job of zookeeper is to keep track of which one is down and which one is up. Okay, now all of the nodes or all of the Kafka nodes, okay, so whatever Kafka nodes we have, let's say this is one Kafka node, this is another, this is another, this is another, they will keep informing to zookeeper. Okay, they'll all keep on informing to zookeeper. Okay, they are saying yes sir. Okay, yes sir. Okay, everywhere you can think of them as informing with yes sir. Okay, if one of them, yeah, continuously they're informing to zookeeper that hey, I'm here. In case one of them do not say, okay, so here under zookeeper's node here, say slash nodes, okay, there will be a, b, c, d, and so on. So if it is a, it is b, it is c, it is d. In case one of these nodes go down, their name will be removed from here because this list keeps on expiring. Okay, and this list, since it keeps on expiring, and if a node goes down, it won't be able to say yes sir to zookeeper, and zookeeper will assume that this is absent, and that's what it will inform when something happens. Okay, so let's say it's not able to say yes sir, and C is dead, and I mark it with, okay, I mark it with this. So here it won't be in the list, and therefore the list will be given back to Spark will be A, B, and D, not the C. Okay, so this is how the zookeeper works. So these are, you can say, these are what we call the Kafka brokers as in the nodes on which Kafka queue is running, because Kafka queue itself runs on many machines. So Arpan's question is, does Zookeeper store what is stored on a particular Kafka broker? I mean the topics. No, it doesn't. Okay, no, it doesn't. All right, that's the duty of Kafka most likely. All right. So here we are saying Kafka utils dot create stream ssc jk quorum. Okay, and we say that this program says that read to a topic called one. Okay, okay, read from a, so Kafka queue is made up of many topics because Kafka is used by many people in organization, so everybody can create their topic and start talking on it. There will be listeners and talkers. Okay, so all the listeners will keep on listening to whatever talkers are saying, and there could be many topics. All right. So here we are saying that listen to a topic, and once we have got this KVS, which is basically the stream. On top of it, we can run many kind of uh, all kinds of operations: map, flat map, filter this, filter that, and so on. And then we could reduce by key. So it's basically doing computing the word count. And again, we are saying counts.pprint. So every time, for every RDD, temporary RDD called dstream, this function is going to get executed. Okay, so let's see up to what we have created. And once we have done this, the next thing would be to log into this folder and try to run Kafka. So here what we have we done? We have created a topic. We have created a topic called we've created a topic called test. Okay, before we are running anything, let's create a topic called test. Okay, so what we do is we do this. All right, we go to the console, we execute this. It says that this is not found, so a better idea would be to put this in our home for our path. Okay, so we say export path equals to $path colon this. Okay, and then I can say, oh, it is still says that, let me see if I can find, there is no such directory. Good. So user HTTP current and Kafka broker. All right, let's see if it runs. All right, let's go to this folder. Oh, it's not existing. All right, let me just check why it's not running. All right, let me just think about it. All right, let me do an SSH. All right, so let's SSH into my account. Okay, and all right, all right. So I've logged in here, and let me just try to locate where did my script go. Wow, it's not able to find. All right, all right. So let me just figure it out because of the version changes. Things have changed. All right, I think yes. Should we check? Yeah, let's check the demo tomorrow with a quick review of the integration. All right. So the general idea is here. I'll just give you a quick review right now, and then we'll discuss tomorrow. So what exactly am I trying to do? First, I wrote a simple program which reads from Kafka and does the computation per second, does the word count per second. That's first program I wrote. Then we will log in into one server and then create a topic, okay, and check if the topic is created. Then we will have something called producer, Kafka producer, which will keep on creating the data, okay, and then we will have some Kafka consumer, okay, and this consumer will basically it will just for testing the consumer if the producer is produce something or not. This is just for testing, and then it will be that's it. Okay, this is just for testing. So producer will produce data, okay, and then Spark streaming will consume it. And here this is one producer. This is the way we are going to use producer here. Yes command is going to print y continuously, and that's going to go to the producer, and producer is going to put all y and so on into this topic called test, and that's pretty much okay. Once we have producer and this producer running continuously and pushing data into topic called test, then we can do Spark Submit with Spark Assembly for Kafka and run our Kafka word count. And it will run happily and find out information about this port using JK Zookeeper. Okay, that's how this works, and we will look into it tomorrow. And these are the various functions supported by Spark Streaming. Okay, and there are some very interesting function called update state by queue and few more detailed function. This function is quite important. I'd like to detail it tomorrow. All right. All right. So thank you very much and see you tomorrow. All right. Bye bye. Have a good day. Thank you, Sekhar. All right. Thank you, Arpan. Thank you, Gridhar. Bye bye.